Okay, today I'll be talking about dbus in the kernel, about a project that a couple of colleagues and I started called kdbus. Everything's good. Precisely Greg, Daniel, me, Kai, and with some help of Tijun. We have so far never spoken about that in public. We have posted a couple of things on the internet, but this is our first talk about this. This talk's going to be fairly technical. But then again, we'll probably only touch the superficial bits of kdbus, since there's a lot to talk about, and yeah, we can't go into all the details simply as a matter of time. I wouldn't be surprised actually if we don't make it through all the slides anyway, but that's okay. If you have any questions, totally interrupt me right away. I'd rather prefer having a discussion constantly going rather than just questions at the end. So yeah, just show up and interrupt me. I'm totally fine with that, and I welcome you if you do that. Okay, then let's get to the technical stuff. What's interesting to notice is that on Linux, we never had a proper IPC, which is quite in contrast to most new operating system kernels or operating systems that have been designed. And most of them, there was IPC at the beginning, and then everything else was built around that IPC. For example, if you look at the Mac kernel, like it's used by macOS or at QNX or Herd, or actually even Android, they all have a very powerful IPC system in the beginning, and then build everything around that. We never had that on Linux. What we had were IPC primitives. And those primitives were really just what the name says, relatively primitive. They were FIFOs and AF Unix sockets, which are basically, I mean, there's no concept of method calls or anything like that. They're just streams, which is, I guess, the Unix way, but it's also kind of surprising that one can build an operating system out of that. With kdbus, we try to, at least we hope, that we can establish an IPC system that is as good as the IPC systems that those operating systems that build everything around it have, and so that we can continue building our operating system around that as well. Yeah, dbus. At this point, I figure most of you will probably know. dbus is basically the most established IPC system that we have in Linux. It's quite ubiquitous in the desktop anyway, and also for system-level software. To clarify what I mean by the word powerful in this case, and that makes it quite distinct from the IPC primitives that Linux has, like FIFOs and sockets and shared memory and things like that. Here's a quick rundown of the stuff that dbus does, just in case you don't know dbus that well or I don't know the details. So it is method calls transactions. A method call transaction is basically just you call some method on some other service and you get a reply for it. That's all that there is to method call transaction. That's already something that dbus gives you at the most primitive level. It has signals. Signals is a concept that you can actually send out messages notifying the rest of the system about stuff. Then you have properties, which is something like, it's newer object-oriented languages tend to expose. It's basically something like a field, like a variable on a property. And there's a scheme how you can have these properties, how you can notify others about changes for these properties. All that together makes it a really OO language. Like you have objects, objects have interfaces, interfaces have methods. Like you would know it from any kind of programming language like Java, right? Like the distinction here to make is that doing dbus is a lot actually like programming in a high-level programming language like Java. It uses the same concepts and just exposes the generally accepted things that we have in these areas nowadays just as IPC. For other clients to access. There's broadcasting. It's kind of related to signals. It basically means that a process can send out a broadcast signal telling everybody about changes. And that's kind of important in dbus, and other clients can then subscribe to these changes. And it's relatively efficiently done in the way that you have matches that you can only get notifications about a specific subset of these events, so that not all processes have to wake up every time something changes, but only the processes that are actually interested in it wake up. There's discovery, which is really useful, so you can actually figure out what's actually on the bus, like which services, what's available. There's introspection. which means like when you know that there is a service, you can actually look into it and it will tell you, okay, I have these objects, I have my objects have these interfaces, my interfaces have these methods, signals, properties, and so on. It has policy, which is also a very important thing. So after all, we're building an operating system here which tends to have privilege separation. You have a couple of system-level daemons and of unprivileged user space daemons that run as normal use and they want to access things on those system services, but that needs to be subject to policy, right? Like not everybody should be able to ever do anything. For example, let's say a network managing service like Network Manager would provide privileged operations to reconfigure the network, but would provide unprivileged operations to figure out if the machine is connected to a network at all. Right? This kind of policy is built in. There's activation, which is a powerful thing to make sure that the system runs with minimal resource usage. Activation basically means that at boot up, you don't have to start all the services that are provided, but you can just delay them until they're first used, until they're first requested, until the first message call or whatever is done to a specific service. There's synchronization, which is a more of the exotic feature in DBus. Basically, the way discovery works is that you have names there, and these names can actually be used as kind of a mutex thing, that people can acquire a name, and this can be done atomically, and people can like the ownership of the name works a little bit like mutex synchronization. There's type-safe marshalling. So in contrast to FIFOs, which basically make no requirement at all on what's actually going to be transferred, DBus implies a certain kind of marshalling so that it's clear. I mean, I'm not sure if the term marshalling is known. It's basically, marshalling is the same thing as serialization. It just means that you find a binary presentation for your objects like integers, strings, and all these kind of things, structures, arrays, that they have a clear mapping to some binary format that you can actually send over the DBus transport. So it has that. It's kind of powerful, and it's type safe, so you actually have a very clear type system that says this is a 64-bit unsigned value, and this is a string, and this is the object path, and these kind of things. There's security. By security, in this case, what's different from policy here is that you can actually query the identity of everybody on the system, so you actually know the user ID, you know the PID of a peer that sends you a message, and you know the security label, like SU Linux security label. It is monitoring, so you can actually connect to the IPC system and figure out what's actually going on right now, like who's sending out messages, who's talking to who replies with what. I already made this point a bit. It exposes APIs, not just streams, right? It is much closer to the high-level API system that a programming language like Java would expose, and much further away from the basic building blocks of streams that are used underneath. Passing of credentials I already mentioned. File descriptor passing, which is a powerful technique, how you can basically pass resources across security boundaries and these kind of things. It's language agnostic, like everything that DBus does, like all the concepts like interfaces and objects and things like that, are viable from all programming languages, and that actually works quite well because DBus actually has bindings for almost any programming language there is. It has a certain level of network transparency. That doesn't mean that you wouldn't notice that there was a network. We still have to explicitly use the network transparent mode, but you can use DBus fine across normal sockets, like IP sockets, and it will just work. One interesting property is that there's no trust required. So if you have a client and do a message call into something else, then unlike with almost all other IPC systems, there doesn't need to be a trust relationship, right? It doesn't have to be the untrusted client and the trusted server, but actually it can be the untrusted client sending something to a completely different untrusted server, and it doesn't have to trust that it does the right thing. It's basically the messages are self-contained. They will not change underneath the receiver. And yeah, it's both ways completely secure in that way. And because the kernel always adds the identity information in a reliable, unfakeable way, they don't have to trust each other. And they know that when the kernel identifies one of them, they can trust them. There is a high-level error concept, which is quite interesting because, I mean, we always, like, error handling is a messy thing, and on Linux we traditionally used on the lower level bits the Arno variables, but they're not very expressive. In dbus, all of that is cleaned up, and you have this error structure. So yeah, this is just a rough overview. I could probably add a couple of more bullet points there. It's just to get an idea why dbus is useful and why dbus is better than just writing your own IPC system based on sockets and things like that. So if dbus is so great, of course, then let's ask, why do we actually need kdbus? So let's have, by the way, again, if anybody has any questions, totally interrupt me. Don't hesitate. So what are the limitations of dbus that we saw and that we wanted to fix? One thing is it's suitable only for control, not for payload. This basically means with dbus you can make method calls in a great way, but you cannot actually include huge amounts of data in it, right? So if you, let's say you would write a sound server with dbus, so far you could totally issue the control messages to change volume and things like that fine with dbus, but if you actually wanted to start to send the audio samples over dbus, then you would quickly notice that that's not a good idea. It is also quite inefficient, right? If you do a full method call transaction with traditional dbus, you get 10 full method copies, right? Message copies. What happens basically is that if a client wants to send a message call to somebody else, it will put together this message, like marshal it into a piece of memory. Then the dbus library copies that piece of memory into the socket buffer. Then from the socket buffer, that's already 2 copies, right? Like from the data that the application ate into the message and from the message into the socket buffer. From the socket buffer, it is copied out into the dbus daemon. From the dbus daemon, it's copied out into the next socket buffer that is for the destination socket. And from there into the other side that receives it. Those are already 5 copies. And then for the answer back, you get another 5. So all in all, you get 10 memory copies of every message. That must be slow, of course. You get also 4 complete validations, right? So because, as mentioned, it's a system where peers with different privileges exist, every message needs to be validated. It needs to be checked that it's actually in a valid form before people go and pass it blindly and trip up on it. So the way how it currently works in dbus is that there are 4 complete validations in that transaction. One complete validation where basically all the marshalling is checked all the way from the beginning of the message to the end is done in the dbus daemon when it receives it, and then after it's sent the method call to the service will validate it again, and then again for the method reply you get another 2 on the way back. So you get 4 complete validations. You get 4 context switches. Context switches in the sense that the scheduler will schedule a different process, right? Because if you send something, then you have first your sending process has to switch to dbus daemon. The dbus daemon process has to switch to the receiving side. The receiving side has to switch back to dbus daemon and dbus daemon back to the original sender, right? So you have 10 copies, 4 complete validations, 4 context switches. That, of course, is not very efficient.
Are you going to talk about why we can't optimize that instead of putting everything into the kernel?
Well, the way how you can optimize that.
If we could rephrase questions before we answer them, just so that we pick them up for the live feed, that would be.
Okay, so the question that was raised is, was whether why we cannot just optimize that instead of moving everything into the kernel. So my response to that, our way of optimizing that is to move it into the kernel, right? Also, we don't move everything into the kernel as you suggest. We just move a certain part of it. There's still quite a bit of user space involved. But the problem is generally there is like the basic building blocks that you have in Linux for IPC, FIFOs, sockets, shared memory, cannot provide enough that you can get rid of those.
Well, but maybe it would be useful to have a zero-copy IPC mechanism.
Exactly, we have that. It's called kdbus. I mean, what would you suggest? The only zero-copy thing you can do is shared memory, but with shared memory you have always intrinsically the security problems that both sides can access the same memory and can basically change the data under the eyes of the other one while the other one is parsing that. It's a systematic problem with security. You cannot get that work. And the other ones you have, like I have Unix sockets and FIFOs, you always have to copy things explicitly into them. So yeah, it's not possible with the current FIFOs. You have to add additional code to the kernel if you want to actually make that work with zero copy. The credentials one can send and receive over dbus are limited. right? There's UID, PID, and GID. Well, actually, the GID is not even exposed, and there's a security label. That's about it. Sometimes one would want quite a bit more. What those are, we will see a little bit later. There's no implicit timestamping, which is sometimes problematic if you get messages from quite a few other peers. Timestamping is essential so that you can order them and know what came before what. There is dbus is something that is only available in late boot, right? If you build operating systems like we always do, we always have this problem. Yeah, if we are in early boot, if we are in init.rd, if we are during shutdown, we cannot use dbus IPC because it's simply not available because the daemon is not running, and it's really difficult to pull it in front, because you always have the security, like for the init.rd, you have to replace it. And the other problem is that then activation, the way current dbus daemon does it, would activate the services way too early. And yeah, so it's a problem for us, basically, that it's not universal, that it's only something that's very late during boot. And that's a problematic thing if you want to have an IPC that every component can use, even if it's, I don't know, a storage manager running in early boot. The hookup with security framework happens in userspace. I mean, I personally don't really care too much about those security frameworks. Those security frameworks as SE Linux, AppArmor, and these kind of things. But the security people always dislike the fact that if dbus security, policy decisions are made and those are hooked up to the SE Linux policy, the AppArmor policy, then the decision about that needs to take place in user space. And the kernel people would usually, like the security people, would always prefer it if all these decisions can happen in one place in the kernel, so that they don't have to trust user space. Then there's the other uncleanliness, at least the way I see it in my biased views, that dbus activated services so far were a completely different beast than the other services that run on system, like traditional System 5 init script services, right? The traditional System 5 init script would be forked at boot time and then would just stay running, and their environment would have to be set up manually and via the shell script. But in the dbus activated case, you get basically the execution environment set up by dbus daemon, right? And from our perspective, we think that regardless how you talk to other daemons and how you activate it, if you activate it via sockets, via bus names and kind of things, you should probably run the same execution environment. Another issue that many people at least see with dbus daemon is that the code base is a little bit baroque. It's a little bit, let's say, over-designed. It's very object-oriented and a little bit over the top, like you have a couple of layers of transports and things on top. The fact is, nobody likes to use the classic dbus library. There's used a lot of XML, like for example, the policy is expressed in XML, and it's really awful. The XML is used for introspection, these kind of things. Some of these XML users are probably okay, but especially the XML policy is something that nobody ever got right. And we had it quite often in the generic distributions that some package mocked around with the policy and resulted in some other package security hole because they opened too much of the traffic. So yeah. And this is a small one here I added at the end. What's really not nice is if you talk about activation of services, then which basically is mostly focusing on that they get started when they're needed, then the other side of the medal is usually that you want to terminate them when they're not needed anymore. And you cannot securely, safely, without losing any traffic, do that with classic dbus, because basically when you decide I'm idle now, you try to disconnect from dbus, but all the messages that are then still in the queue that you have not read will be lost. I'm not going to go into much more details, except that it's horribly racy in current dbus and practically not possible. Yeah, we would like to fix that too. There are a couple of more things that's problematic with dbus, but these are the major ones. I think that the top two are the primary drivers for what we did there. So, given those limitations, let's underline that dbus is actually fantastic and it solves real issues, right? We believe the concepts that it introduces of services, of objects, methods, signals, and all these kind of things are absolutely well designed and are the things that we believe make a lot of sense. I mean, dbus was designed 10 years ago, right? And by now we do know from having worked with it for 10 years is that, or I don't actually know if it's actually 10 years, but it feels like it was 10 years. It's actually 10 years. So it feels like we nowadays know that, sure, it might have shortcomings, but the shortcomings are not in the general concept. The shortcomings are in performance and the other things that I just pointed out. So it's quite comprehensive. It covers everything, right? We build an init system with it. We build a desktop environment with it. People build it into cars and these kind of things. It covers pretty much everything. It's not like a specific solution, like, for example, the Android binder is, which is optimized for ARM CPUs and these kind of things. It's a solution that really covers all the grounds, basically what Linux covers as well. It's also quite established, right? It's a single most used local high-level IPC system in Linux, and it has bindings for most languages. I mean, people have come up with quite a few different local IPC systems like Corber and whatnot and DCOP. But at this point in time, I think it's absolutely safe to say that on Linux, at least on traditional Linux, if you look at Android, of course, Android binder is more established. But on traditional Linux, there is pretty much nothing else but dbus that people generally use. As mentioned, it covers, like, it has found its uses all the way from the system to desktop and so on. Okay, so yeah, I hope at this point you have an understanding why we believe that dbus is the conception of the right thing, but has certain shortcomings. And we'll come to kdbus now to explain you what we do better, or at least believe that we do better than a traditional dbus. Any questions up to this point? You guys need to ask more questions. Okay, so kdbus. From the beginning it's suitable for large data, right? You can send gigabytes of memory over it. It supports zero copy, even though it will not do zero copy by default. Why? We will tell you later. This memory that you, like these large data blobs, are nothing that you have to send once and then cannot reuse. There's actually an entire concept built in that you can actually, for example, send the same memory, like an image, a couple of times, and that's highly efficient. It's anyway totally efficient because you remember that slide where I said 10, 4, and 4? For us, it's 2 or fewer copies, right? For zero copy, it's 0 copies, and in the normal case, it's actually 2 copies. There are 2 validations and 2 context switches, right? Again, this is for a full duplex method call. There's a typo, method call transaction, which basically means, yeah, you make a call, that is 1 copy, and you get the reply back, and that's another copy. And because every peer needs to validate the message from the other side because it can trust it, you have those 2 validations, and you have 2 context switches because you first switch to the other side, and then you switch back. So it's pretty much near to how few you can actually make there.
Does the kernel not manage validation on the receiver?
So the validation is done by the receiver. So this goes a little bit further into what we're talking about later, but so basically the design that we picked there is that the kernel only has a very superficial idea of the marshalling. It will only know the basic, the outside routing, right? It knows where the message needs to go and where it's from. It does not know anything about the contents. It doesn't know anything about what array you attach to it or variant you attach to it, and it shouldn't know that, right? The kernel, that's a nice design feature. Okay, so the credentials that are sent along are comprehensive, right? There's everything in it. You can have UID, PID, and GIT, like you can have traditionally in SLinux labels, but you can also have the PID start time. PID start time is actually kind of useful because if you combine it with a PID, it kind of solves the problem that PIDs are reused, so you can actually use that for security purposes. There's a TID. The TID is a thread ID on Linux. There's a COM field. That's a process name, as you see it in top. There's a TIDCOM, which is a thread name. There's argv, which is like the command line. There's exa, which is the path to the binary, and C groups and caps and audits. We added all of these. Some of them are highly useful for security purposes. Like, for example, the audit stuff is something the audit people wanted forever, because then they actually can log audit information every single method call. But our personal reason why we personally wanted that is that we want to build the journal's log client based on this, because then we can, in a race-free fashion, get the identity of the sender and log that away, so that every message is stored with information about these kind of things. But this is also very useful for things like PolicyKit, because from the C group you can identify the session that something comes from and these kind of things. So yeah, that has quite a few uses. There's implicit timestamping. Whenever a message is sent, the timestamp is taken. It works a little bit like timestamping works in network packets these days, and you can query them. There's actually like 2 timestamps always taken, the monotonic and the real-time clock, so they're useful for a lot of purposes. It's always available from earliest boot to latest shutdown. It's basically our client side, we'll come to that later, is built into systemd, and systemd will set it up really, really early on. So basically, the only time that the system exists without this IPC working is this really short time where systemd has not started any process yet. Yeah, so effectively this means IPC is for the first time available from all the way that user space exists to all the ends that it stops to exist. Because it's implemented in the kernel, it's open for LSMs to hook into that from the kernel side. The activation that we did with KDBus tries to copy concepts that we have with socket activation. So with this, dbus services stop to be special regarding activation. There, you can basically have a service that is socket activatable, bus activatable, hardware activatable, and whatnot activatable, and everything's handled the same way and executed in the same execution environment, and your service doesn't have to care how it got activated. It just knows that some reason was there, and it can actually figure out which one that is if it cares about that to be started. The user space is much simpler, and there's no XML anymore. Well, there's some XML for the introspection stuff. We couldn't get rid of that. But for the policy, at least, that's gone. And yeah, this other little thing, you can do race-free exit on idle for bus-activated services, which is something I personally care about. There's probably a couple of more of these. Yeah, so that's a high-level overview. Why? Now let's, unless there are any further questions, you guys need to ask more questions. There's a question.
Do you envision that dbus is eventually going to be just a shim on top of kdbus? Is that where you're going with this, or?
So the names is a difficult question because some people. So the question was regarding, if I understood correctly, whether dbus is going to be a shim around kdbus. I think there's a question about naming things. For us, dbus is just a concept, like a generic concept of IPC, and kdbus is pretty much compatible to that, right? It's just a re-implementation of it. There are some changes if you connect via kdbus instead of via the old one, like you have to care for a different policy. We will come to that. But basically, I assume that a system in from 1 year or so will basically use kdbus for everything. The clients will talk directly to kdbus, and if there are legacy programs like statically linked binaries and things like that, then they will connect via some proxy, which we will also still come to connect to traditional kdbus. But basically, it's going to be kdbus and little else.
So the expectation is if I have a Python application today that uses the dbus bindings, then this is going to be dropped in and I'm not going to have to change anything about the application?
Yes, so the question was regarding whether you have a Python binary, if you don't have to change anything, if you just want to keep it running on kdbus. Yes, you do not have to change anything. I mean, there are some, yeah, basically you have to not to change anything. There are very limited differences, like regarding the policy, but you can even ignore that. But regarding timing, and that sometimes you might be capable of figuring out that you're not running on a real dbus daemon, but on a fake one. But those are niche cases, and I'll bet you $50 that you're not going to find that.
Tell me to be patient if you've got this later on, but have you got any performance tests showing?
No, we don't. So, I mean, the state is, well, let's talk about that later, but we don't. Anyway, any further? There's a question.
Those advantages that you just listed, do they rely on kdbus being tied into systemd?
Well, I mean, our user space, the user space that we wrote, is built into systemd. But people can write other user spaces. There's no problem in that. Like, the stuff is completely generic. There's no, I mean, there's no requirement from the kernel at the user space side of systemd. That would be crazy. But our code is bound to systemd, and it involves a lot of concepts that are systemd concepts. For example, activation is implemented as a unit. which in unit is a systemd concept. So I don't know. We will not work on anything outside of systemd. If people want, they can certainly do that. Everything is documented, or at least roughly documented. I mean, it's relatively new stuff, so all that you might need to ask us in some cases. But people can write that. You can probably even salvage some of our code and make that work. But I'm pretty sure if you want to use it outside of systemd, you have to do your own work first.
But some of the advantages that you talked about, like not using XML configuration files, are they systemd advantages working with KDBus, or are they KDBus advantages?
Well, again, this is the entire user space that we wrote is inside of systemd, and that user space does not use XML for the policy anymore. I don't see why you would want to use, even if in a different user space implementation, I don't see why you would want to use XML for that configuration bits. In particular, because the policy is one of the few cases where we are quite different from the original dbus design, because the original XML policy language was so badly designed that we wanted to get rid of it. Any further questions at that point? Okay, no.
Just repeat the question when you're giving the answer.
Oh, sorry, yes. Was that clear? Do I need to repeat the other one? Okay, so about the technical details now. This is going to get quite technical now. The way how this all works is basically KDBus is by design, it's a character device that you find in /dev. So it feels a little bit like a device driver. You open that thing, and then you basically get a file descriptor out of it, and you can take that file descriptor and memory map it. When you memory map it, you basically just set up a memory arena where the kernel will then drop the messages that are intended for you into. And then the kernel will tell you where it placed it, and then you can read it from there. Right? So every receiver has its own buffer set up like that. And when you send a message, what happens is basically it just tell the kernel, OK, copy the message that I have prepared here in this my private area into the receiver buffer of that other peer. And then the kernel does that, and that's it. And that's basically the entire design of how we do these transactions. That's why we can do single copy message transfer. Because we don't need to copy something into the socket buffer and then out of the socket buffer into the destination. All we do is we tell the kernel, OK, copy this bit directly into the receiver buffer on the other side. These receiver buffers, because they're actually tied to the file descriptor that you have, you can actually pass a file descriptor around and have 10 people memory map the same buffer, and they can access the messages they receive with that. Yeah, as mentioned, this is single copy to destinations. This is for the case where you have a small message, you want to give it to somebody. There's a concept called method called windows. A method called window, it's a time window basically, where if you send a message to somebody else, where that somebody else is allowed to send back a message to you. And yeah, so it's basically, it opens a hole in the policy so that you can send one message back for every method call that somebody made so that you can send a reply back. This window also has a couple of other implications. For example, there's a timeout attached to it. So if the other side doesn't decide not to send a reply back, you get information from the kernel that this timed out, then the window will be closed, and you can know that the thing timed out, the other side didn't respond. So yeah, there's a name registry. The name registry is very close to how the traditional dbus name registry worked. Like, name registry is about service names here. So basically that Avahi gets the name, hello, I'm Avahi, and network manager gets the name, hello, I'm network manager, and then the kernel keeps a list of that. And it's what the kernel does here in KDBus is actually very, very close to how the traditional method worked, like the traditional implementation dbus daemon worked. However, it's a bit more powerful, like a couple of new concepts like activators and things like that. But we'll not go into the detail for that because I don't have the time, and B, that you probably only need to know about these if you actually implement a user space, a second user space implementation of all of that. Another concept that we introduced is memfds, right? Memfds are for, I mean, we just talked about the receiver buffers and the single copy data transfer. Memfds is a concept that we use for the zero copy transfer. A memfd is a very simple concept. It is just a file descriptor on a piece of memory, right? It's basically similar to opening a file in /temp, immediately deleting it and mapping it into memory, but keeping the file descriptor open. And then you can send somebody else a file descriptor, and he can map this as well and look into the same data. And as soon as everybody closed the file descriptor and unmapped the memory, it's gone. MemFDs are a lot like that, but also very different. They are different in this particular feature that they support something called sealing. The sealing is basically that if there's only one file descriptor open for one of these MemFDs, and nobody has mapped it, then it can be sealed, which basically means that nobody can change it anymore until it's unsealed. The reason why we have that is basically that if you prepare some large message, like sample data or video data or whatnot, wanted to send to somebody, then both sides need a bit of assurance, right? The sender needs to be sure that the receiver cannot change it, because, I mean, if you would do it with the temp file thing, he could. And the receiver needs to be sure that the sender cannot send it anymore until after it's sent it, right? Because both of them have to parse the data or reuse the data, and they need to make sure that the other side cannot change things underneath, confusing the path that you have. That's quite a security feature. What's interesting, so we use this basically in KDBus, these MemFDs, partially in a completely transparent way that the client will never actually know that MemFDs are used underneath. So what happens actually if you build a message with a KDBus client library, what happens is that all the message data is actually first put together in a MemFD, right? Then when we figure out that the MemFD is full over a certain threshold, we will seal that MemFD and send the MemFD over to the other side instead of the actual message itself. However, if the message stays under that threshold, we will copy the message directly, right? That's a distinction between zero copy and a single copy here. If it's small, we do single copy. If it's large, we do zero copy. The interesting thing that we figured out is that the threshold actually needs to be at 512 kilobytes, where zero copy is faster than single copy. Before that, single copy is faster than zero copy, actually. The reason for that, which, I mean, it sounds surprising that doing one copy is cheaper than doing zero copies. The reason for that is simply to do that zero copy stuff, you actually need to map it on the other side. Now, mapping files is while after you mapped it, access is quick. Actually, the mapping part of it is expensive because it flushes TLBs and these kind of things. So we actually ran a couple of tests on a couple of different CPUs to figure out when is it slower to set up a memory region, map it first, then put the data in it, close it, like seal it, send it over, open it again, and map it. When is that operation slower, which involves two memory maps and two memory unmaps, then, how long is that slower than simply copying the data over directly without any mapping involved? As it turns out, on pretty much all CPUs that we tried, like from Intel CPUs to PPC, and even ARM or something, it always ended up to be around 512K, where the simple copy to the other side is quicker than actually passing those MemFDs around. So again, putting this together, what happens actually is like the sender always puts stuff together in a MemFD. When it figures out at the end, when the message is fully put together, that this is under a certain threshold, it will just copy the bits, right? Like if it's under 512K, we'll just copy it directly into the receiver buffer, the kernel. However, if it's larger than that, it will instead just send a tiny stub of a message and say, okay, the actual payload of this message you find in that MemFD. And then the other side maps that. Now, this concept is mostly hidden in the library. You never know that what's actually sent there, and it's not relevant to the applications because we actually do the fastest thing for you anyway and blindly. However, the MemFDs are also exposed in the API so that applications can make direct use of these because for a certain use case, it makes sense to reuse MemFDs, right? For example, I wrote Pulse Audio, as you might know, and in Pulse Audio, we have a sample cache, right? Like if you have, for those click sounds, we keep the click sound in a buffer, and then every time you click, instead of loading this thing again and again, we put in a sample cache and just play the same memory again and again and again. This actually maps nicely to the MemFD stuff, because basically, yeah, you just load the sample, put it in the MemFD, seal it, and then every time it's played, you just pass that file descriptor to the actual daemon, and that's it, right? And because of the sealing, it's completely okay. Nobody can change anything, and it's safe and secure. the concept of memfd is not unlike something called Android ashmem. Ashmem is something that Android people, I mean, it's not part of Android Binder, but they usually use it close to that. Ashmem is nothing that is implicitly used by Binder or the client libraries. It's something that is explicitly used by applications. Ashmem is very similar again. It does not support the same concept of sealing. For Ashmem, only one side has to trust the other side, and the other side can be sure that the other one can change. So it's a one-way trust relationship, while for us there doesn't need to be any trust. And it has a couple of other concepts like that you can destroy it and things like that, but we'll probably get that on Linux kernel with volatile ranges and whatnot, so that's a completely different story. So yeah, if you look at Android Ashmem, it's a very similar thing, but ARM MFDs are different. Ooh.
Lennart, is there any implication in unswappable memory areas for the kernel with leaving sealed objects in KDBus?
Well, I mean, everything that KDBus does. The question was unswappable memory and the sealed messages. So that's not really a problem because everything that KDBus does, regardless if it's a receiver buffer or these memfd things, is actually backed by tempfs. So it is swappable memory always. So yeah, it's basically like having a file in /temp. It's very, very close to that.
It's memory of the process, not of the kernel.
So I don't have that much time anymore, so let's quickly glance over signal broadcasting because it's technically kind of cool. I already mentioned that on dbus you have these broadcasts that you can send a signal to everybody, and then everybody can have specific filters on that and get only be notified and only delivered those messages that it is actually interested in. We implemented that in KDBus with something called Bloom filters. Bloom filters is something, it's used quite frequently, like for example, the glibc dynamic loader uses this technology to, like this idea, to speed up symbol lookup in libraries. So what it basically does, and Google uses it, for example, if you type something into the Google search mask, it will check against a Bloom filter if that query has any chance to actually succeed. What a Bloom filter does basically, it's a piece of memory that you calculate from a big vocabulary, and it involves hash functions basically. And then later on, you can test one word against this Bloom filter, and it will tell you probabilistically that it's either inside of the Bloom filter, which means probably if you actually now go to the disk, you will find it, or it will say no, it's not in there. So the not is not probabilistic, the yes is probabilistic. I hope you guys could follow. If you want to know the details about Bloom filters, actually read up on Wikipedia or something. Bloom filters have been used before in libudef for the notification, because in libudef you have the case that different apps are interested in different parts of devices showing up. And so we already used that like 5 years ago. We added that to libudef. So basically, every message comes with a Bloom filter where the vocabulary used is every possible match that clients might have on that message. And then the message, then the receiver just installs a mask that needs to be tested against that Bloom filter. It's really nice stuff, actually. So for broadcast messages, we always attach a Bloom filter, and then the receiver side is calculate a Bloom filter mask, and then tell the kernel about it. For the kernel, doesn't know much about Bloom filters. For the kernel, it's just a field of bits, basically, that it needs to mask against, but userspace can make more sense out of it. So yeah, I think I'll skip the policy part. The user space side, as mentioned, lives mostly in systemd. There are a couple of components involved. There's a proxy. The proxy basically provides compatibility with the old socket-based interface. Everything the proxy does is you have a couple of instances usually running of that, and it will listen on the traditional socket, like var, lib, dbus, system socket bus, or something like that is a socket call. And every message coming in will be forwarded to KDBus, and then KDBus response will be forwarded to the client, so that the client doesn't have to know that KDBus is involved, and it appears to KDBus, those clients basically that talk to a traditional dbus daemon. It's only exists for compatibility, and it's probably going to go away soon.
If you recompiled your program
Okay, so the question was if you don't recompile your stuff against traditional libdbus, whether kdbus is used or the proxy is used. The answer to that is that currently there is no port of libdbus to kdbus, so it will always go via the proxy. However, there are people from Samsung working on making traditional libdbus work on kdbus on top. And then, of course, the logic is going to be, kdbus is preferred and the sockets are only the fallback. But there are some differences, like I said, some issues with that involving policy because our policy is different. And for the session, that's what's going to happen because in the session there is no policy, but for the system it's a little bit more complex. But given that I don't have much time, Okay, let's, given that I have 1 minute, let's finish off with one slide. I mean, again, it's not a problem that I did not expect to make all these slides. It's a lot of to cover. A lot of ground to cover. But I hope at least you got the ideas of the concept of the Bloom filters a bit and of the MEMFDs and of the receiver buffers. So let's finish with one slide regarding the when. We have been hacking on this for the last month. And we have announced like the first working system, working implementation of all of this a couple of weeks ago on the dbus mailing list. If you want to know all the details, just look up on the dbus mailing list and you'll find a longer text that covers a lot more ground than I was just telling you about here. It probably takes a little bit longer to go through than just 45 minutes. The code's all there. It's pretty much completely implemented. The only white space still missing is basically policy. The good thing about policy is that while all the other features make things work, policy is usually just about making things not work. So you can totally boot up a system without policy and everything will work. Of course, it will be horribly insecure, but who cares about security anyway, right? Yeah, the policy is still the white space. We are working on that. I have on my machine, on this one, actually, I have already most of the client side working, and we've figured out most of the kernel side as well. It's a compile time switch and systemd to make use of this. So the reason why it's a compile time switch is simply because we don't want clients to assume that kdbus the way it is currently will work in 5 years because we want the freedom to change it still. We hope that the kernel side is going to be reviewed and accepted into the kernel in 2014, like in the current year. Given that Greg is involved and that we managed to get Tejun on board for reviewing everything, we kind of hope that it's going to be relatively smooth ride. Then again, 2 previous attempts to get dbus into the kernel already failed, but we are hoping the best. GDbus support is being worked on, like in glib. As mentioned, some of the people have been working libdbus 1. I didn't put the URLs for the Git repos here because you can Google for them, and that's all I have. Thank you very much.